Hello everyone. Today I want to talk about 10.2 sequences, the second part. In the previous lecture, we talked about some techniques to evaluate the limit of a sequence. And today I want to introduce one more. It's called the squeeze theorem for sequences. We learned the squeeze theorem for functions in Calculus 1. Okay, basically right here we want to use a similar idea. So right here you have three sequences, the sequence of a sub n, the sequence of b sub n, and the sequence of c sub n. And right here a sub n will be less than or equal to b sub n, and b sub n will be less than or equal to c sub n. Okay, and right here this inequality holds for all the integers n greater than some index capital N. So that means you don't always need this inequality. You just need to make sure that this inequality holds when n is greater than or equal to some number. For example, after the first 100 terms, you will have this. Okay, it doesn't matter if the first 100 terms satisfy this inequality or not. No, we don't care. We just need to make sure that after the first 100 terms, we will have this inequality. Then we are good. Okay, of course, right here I just made that number up. Okay, it doesn't have to be the first 100 terms. It can be the first 1,000 terms. As long as eventually you will have this inequality, then we are fine. Now, if the limit of a sub n as n goes to infinity is the same as the limit of c sub n as n goes to infinity, and both limits exist and their values are L, then we can say that the limit of b sub n as n goes to infinity equals L. Okay, so let me try to draw a picture and to show you what's going on right here. So let's say we have, because we have this relation, okay, so let's say we have this sequence a sub n. Okay, so each dot represents a term, okay, and we have this sequence b sub n, no, c sub n. Okay, and we have something, we have a sequence b sub n, but I don't really know how this sequence behaves. Okay, so it might look like this. But one thing I'm sure is that b sub n, eventually it will be between a sub n and c sub n. Okay, so right here I don't really care how it behaves, but eventually these green dots will be between the blue dots and the red dots. Okay, so you can see that as n goes to infinity, the limit of a sub n will approach a number, and that number is the same as the limit of c sub n. They will approach the same number. Now, since b sub n is between a sub n and c sub n, you can see that b sub n will go to the same number as well. Okay, so that's why we call it a squeeze theorem. So you can see that right here we squeeze, right? We squeeze these two sequences. Okay, so they will be the same value. Now, if you have something in between, just like a sandwich, okay, it will go to the same value. So let's take a look at example 1. Does the sequence converge? Okay, last time we talked about this. Whenever you see this sentence, it means does the limit of a sub n as n goes to infinity exist? Okay, so that means right here we will need to find the limit of cosine n pi over 2 over square of n. Now, in the previous lecture, we have some techniques, right? We say that we can divide both top and bottom by the leading terms in the denominator, right? We say that we can use L'Hopital's rule, and we say that we can use growth rate, okay? But it seems right here those methods won't work, okay? So right here, let's take a look at how we solve this problem. So notice that right here, no matter what n you choose, so for every positive integer n. Okay, no matter what n you choose, your cosine of m pi over 2 is always between -1 and 1, right? So remember the graph of cosine looks like this, right? So you can see that the maximum value of cosine will be 1, and the minimum value of cosine will be -1. Okay, so you can see that the values of cosine changes between 1 and -1. Okay, so we do have this relation. Now notice that cosine m pi over 2 is your numerator. My denominator is square of n, so I want to divide everything by square of n. And right here, since square of n is a positive number, we don't have to worry about changing the direction of the inequality. So we are good right here. Okay, so I want to make this sequence. That's why I divide everything by square of n to make this on purpose. So this is your middle sequence. So you can see that let's correspond to this. Okay, I know it's a little bit confusing because this is called an. Let's just forget this is an. Okay, so this is your middle sequence. Okay, you have a lower bound sequence and you have an upper bound sequence. Just like Bn is the middle sequence, and you have a lower bound sequence, and you have an upper bound sequence. Okay, so you have this inequality. So this inequality, we have this. Now we just need to make sure that the limit of the lower bound and the limit of the upper bound will be the same. Then we can say the limit of the middle sequence will go to the same number. Okay, so right here, the limit of the lower bound is 0 because you divide -1 by a large number. It's 0. And also the limit of the upper bound is also 0, right? It's also 0. 1 over square root of a large number. This is 0. So the limit of the lower bound equals the limit of the upper bound. They have the same value. That means the limit of the middle sequence. Okay, again, right here we don't really care what the sequence, what the middle sequence, how the middle sequence behaves. Okay, I just like this. I don't really care. I just need to make sure that all these green dots will be between the blue dots and the red dots eventually. Okay, so if they go to the same number, then the limit of the middle sequence will go to the same number as well. Okay, and this is by the Squeeze theorem. Okay, by the Squeeze theorem. Okay, therefore, since the limit equals 0, that means the limit exists. Okay, therefore, the sequence, okay, this sequence converges to 0. Okay, converges to 0. So we will choose B. Okay. So again, right here, in order to use the Squeeze theorem, okay, there are two things you need to, there are two conditions you need to satisfy. First, you need to establish an inequality. And then you will check the limit of the lower bound and the limit of the upper bound. Now, if they go to the same number, then you can say for sure that the limit of the middle sequence will go to the same number. Is okay? Okay, let's take a look at example 2. Does the sequence whose nth term is a sub n equals n times sine cube over n plus 1 converge? Okay, if so, to what value? Okay, so again, you see the sentence, does the sequence converge? This means does the limit of a sub n as n goes to infinity exist? Okay. Now for problems like this, it looks like a Schrödinger theorem problem. Okay, it looks like a Schrödinger theorem problem. Now let's say we have a different problem. Let's say we have sine cube over n plus 1. Then yes, this is a Schrödinger theorem problem because this will be between positive 1. Sorry, this will be between positive 1 over n plus 1 and negative 1 over n plus 1. And since this will go to 0, this will go to 0, that will go to 0 by the Schrödinger theorem. Okay, now unfortunately we have an n on top. Okay, we have an n on top. So we will need to take care of this problem in a different way. Okay, let's take a look at this. Now we know that this sine cube, okay, this sine cube is always between negative 1 and 1. Okay, it's always between negative 1. So that's why in the previous work, I say that if we don't have this n, we can use Schrödinger theorem, okay, because this numerator will be between negative 1 and 1. Okay, but the question is, now we have n times sine cube, okay, this n times sine cube. So that means your n times sine cube over n plus 1 will approach sine cube as n goes to infinity. Because you can see, just think, let's say this is a number like 5. Well, of course this is not 5, it's between negative 1 and 1. How about 1/2? Okay, let's say this is 1/2. Let's say we know the number. So you can see that this is a polynomial over a polynomial, right? Let's say this is a number. Assume it's fixed, right? This is a number, and then they have the same degree. So we say that we can take a look at the ratio of their leading coefficients, right? So that would be this guy over 1. So that would be this fixed number, right? So if this is fixed, we know that the limit will be this value. Okay, now of course this is not fixed yet because n is changing, but we know the limit of sine cube as n goes to infinity, this limit does not exist. What's this? E does not exist, right? Because this is the graph of sine function. So when n goes to infinity, basically it oscillates between 1 and negative 1. We don't have a specific value that this graph will tend to, right? So that means we don't have a horizontal tangent line right here. Okay, so that limit does not exist. Okay, now if you take the limit of this, that should be the same as the limit of sine cube. But we know the limit of sine cube does not exist. Therefore, the limit of n times sine cube over n plus 1 as n goes to infinity does not exist. As a result, we know that if the limit does not exist, the sequence diverges. So we have to choose D. Okay, so you can see that the reason we put these two problems side by side is because they both look like the Schrödinger theorem problem. However, right here we can apply the Schrödinger theorem problem because we know the numerator is between negative 1 and 1. But right here we can't because your numerator will be between negative n and n. Okay, so when you apply the Schrödinger theorem, you won't have the same values for the upper bound and lower bound. Okay, so we will need to treat this problem in a different way. Okay, so notice that you have n and n plus 1 because we have the same powers. So basically we will need to take care of this number, okay, this number, but as n goes to infinity, this number does not exist. Okay, therefore the limit of the whole fraction does not exist. Okay, and we know that if the limit does not exist, the sequence will diverge. Okay. Next, we want to introduce a very special sequence, and we will use it. I don't want to say a lot, but it's really important. Okay, so let's take a look at page 2. Geometric sequences. Now, geometric sequences have the property that each term is obtained by multiplying the previous term by a fixed constant. And we call this fixed constant the ratio. Okay, for example, let's say we start from 1, and we multiply the previous term, the first term, by 2 to get 2. And then we multiply the previous term by 2 to get 4. Multiply the previous term by 2, multiply the previous term by 2, multiply the previous term by 2, and so on. Okay, so you can see that we multiply the previous term by 2 to get a current term, multiply the previous term by 2 to get a current term. And since this number is fixed, okay, I don't multiply the first term by 2 and then multiply the second term by 3. No, I always multiply by the same number. Okay, and this 2 is our ratio. Okay, this 2 is our ratio. So let's write it down. We multiply the previous term by 2 to get the current term. And this 2 is our ratio. Okay? So geometric sequences will have the form a times r to the nth power. Okay, so right here a is your first term, and we multiply the first term by r, the second term by we multiply the second term by r again, we multiply this term by r again. Okay, so to be precise, this should be n minus 1. Okay, so let me fix this. This should be n minus 1. Because the first term happens when n equals 1, that will be a. Okay, or if you want to keep a times r to the n, then n will start from 0. Okay, now if you want n to start from 1, then it should be a times r to the n minus 1. Okay, so you can see that the third term, the power is 2, not 3. So 3 minus 1, that will give you 2. Okay, so it really depends on where you start. Okay, but anyway, it will be a number a times powers of r. Okay, powers of r, where r is your ratio. Okay, now of course right here we don't want a to be 0. Otherwise everything will be 0. It's not interesting, right? Everything will be 0. Okay, now of course if r is 0, then almost everything will be 0 except for your first term, right? Okay. So let's take a look at the box below. Now we want to find the limit of a geometric sequence. So basically we want to take the limit of a times r to the nth power. Let's assume n start from 0. Okay, we want to take the limit of that. Now notice that a is a constant, so you can take a out. So that's why basically we want to focus on the limit of r to the nth power. Okay, now we have 4 cases. Okay, so you can plug in some numbers and verify these results. So let's say r, the absolute value of r is less than 1. So you can try 1/2. Okay, you can try 1/2. So the limit of 1/2 to the nth power as n goes to infinity. That means you need to multiply 1/2 by 1/2 infinitely many times. So 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is 1/16. You just keep doing this, and eventually the limit will go to 0. Okay, the limit will go to 0. Okay, again, you can try, for example, limit of -1/2 to the nth power. Now this is a little bit different because you can see the values are oscillating, but eventually it will become 0. Okay, it will become 0. So you can try that when you go back. Okay, so now if r equals 1, so basically you have the limit of 1 to the nth power, but we know that 1 to the nth power is simply 1, and the limit of 1 is just 1. So we have 1. Now if you let r be -1, then we have the limit of -1 to some power. Okay, the limit of -1 to some power. Now, -1 to some power, it means it's either 1 or -1, right? It's 1 or -1, but we don't know which one it is. We just know that it jumps, the values will jump between 1 and -1, but we are not sure which one is the value, okay, of the limit. Okay, again, if we don't have a specific value, then the limit does not exist. The limit does not exist. Okay. Now finally, you can try the case when the absolute value of r is greater than 1. For example, you let r be 2. Right? So you have to multiply 2 by itself infinite many times. So you have 2 times 2, 4, 4 times 2, 8, 8 times 2, 16, and you just keep multiplying by 2. Then eventually it will go to infinity, and infinity is not a number, so it does not exist. It's okay? And we say that if the limit exists, then the sequence will converge. So right here you can see that the limit exists when the absolute value of r is less than 1 or r equals 1. So the geometric sequence is convergent if r is between -1 and 1, including 1. Now the geometric sequence will diverge for all the other values of r. It's okay? Now let's take a look at example 3. Does the sequence whose nth term is an converge? If so, to what value? Okay, again, you see the key sentence. Does the sequence converge? Right? So you want to check whether the limit of a sub n as n goes to infinity exists or not. Okay. However, this is a very particular, this is a very specific problem. So notice that our term is 5 times log 3, natural log of 3 to the nth power. So we can say that this sequence is a geometric sequence. Okay, now you might be wondering, how do I know this is a geometric sequence? Well, take a look at this form. So if you increase the index by 1, that means you increase the power by 1. If you increase the power by 1, that means you will need to multiply this value by natural log of 3. So every time you find the next term, you increase the power by 1. That means you multiply the previous term by natural log of 3. And that is the definition of geometric sequence. Right? So if you want, you can write down the first few terms. When n equals 0, that's 5. When n equals 1, that's 5 times natural log of 3. N equals 2, 5 times natural log of 3 squared. N equals 3, 5 times natural log of 3 cubed. Right? So of course, I don't want you to write down every term, but if this is the first time, you can do that. But think, if you increase the index by 1, you multiply the previous term by natural log of 3 because you increase the power by 1. That means you multiply by natural log of 3. So this is the geometric sequence with a ratio r equals natural log of 3. Okay, with the ratio of r equals natural log of 3. Does that make sense? Okay, take a look at this. You increase the power by 1, that means you need to multiply by nature log of 3. Okay, now we have this very convenient conclusion for geometric sequence. So basically, to determine whether a geometric sequence is convergent or divergent, all we need to do is to take a look at the ratio. Okay, so now we want to take a look at our ratio, nature log of 3. Okay, now of course right here you might be wondering, but I don't have a calculator. How do I know the value of nature log of 3? Well, basically you don't need to know the exact value. Well, basically the exact value is nature log of 3. You don't need to know the numerical value. You just need to know whether nature log of 3 is greater than 1 or less than 1. Okay, so know that 3 is greater than e. Do you agree? Right, e is about 2.7, right? That means nature log of 3 will be greater than nature log of e. But nature log of e is 1. So we know that nature log of 3 will be greater than 1. So thus, this geometric sequence, since your ratio is greater than 1, the geometric sequence will diverge. Okay, this geometric sequence diverges. Does that make sense? Okay, so notice that the reason we can do this without, so see here, I don't really evaluate the limit of a sub n. I don't really do this. Okay, this is because for geometric sequence we have a very good result. Okay, all we need to do is to look at the ratio. Okay, look at the ratio. Now, of course, you say, can I use this method as before? Yes, you will get the same answer. Okay, but that will take you some time. Okay, so it is our suggestion that you take a look at the ratio. Okay, now let's take a look at example 4. Does the sequence converge? Okay, again, does the sequence converge? So of course, you can try to find the limit of the nth term as n goes to infinity. But we notice that this is again a geometric sequence. Okay, geometric sequence. Now, this is the first time. Okay, so perhaps you cannot see through the disguise immediately. So let's try to do some pre-calculus right here. Okay, so first we have 3 to a negative n. So what does that negative sign represent? Here. That means you have to put it in the denominator, right? So we have 2 to the n plus 1 over 3 to n. Okay, and then what does that plus 1 do to our value? That means we can write it as 2 to the n times 2 over 3 to the n. Right? And of course, 2 is a constant, so I can write it as 2 times 2 to the n over 3 to the n. And finally, because they have the same power, I can combine it as 2 over 3 to the nth power. Now you can see that this is a form of a geometric sequence, right? So every time you increase the power n by 1, you multiply by 2 over 3. So this is a geometric sequence with a ratio of 2 over 3. Does that make sense? Okay, so this is a geometric sequence. Okay, this is a geometric sequence with a ratio of 2 over 3. Okay, with r equals to, okay, let's write it down carefully. With a ratio of r equals 2 over 3. Okay, so we will use this result. Now 2/3 is between -1 and 1, so we know it will be convergent. Okay, so since our ratio 2/3 is between 1 and -1, then this geometric sequence, converges to 0. Okay, converges to 0. Okay, now you say, yeah, I know it converges because of this, but how do I know it's 0 or 1? So notice that this 0 happens when the absolute value of r is less than 1, and of course absolute value of 2/3 is less than 1, right? So we have to choose this. Okay, you only have this 1 when your ratio is 1. But notice that this is only the limit of r to the n. You also need to multiply by a. Okay, so in this case, since your r is 2/3, is less than 1, the absolute value is less than 1. Okay, strictly less than 1. So we know the sequence will converge to 0. It's okay? Okay, again, as I say, we will see geometric sequence a lot in this section. So, in this chapter. Okay, so please make sure you know how to identify a given sequence, whether a given sequence is geometric or not. Okay, there are more practice problems on Canvas. If you have any questions, please do not hesitate to let me know. Thank you.